Hello friends, yesterday we have seen the types of the semiconductor. In the extrinsic semiconductor, there are exactly two types, N-type semiconductor and P-type semiconductor. Today we are going to learn about the P-type semiconductor. Now, P-type semiconductor. P-type semiconductor. Silicon crystal. Each silicon atom having 4 valence electron in outer orbit. By sharing one electron, it forms a covalent bond. Each and every silicon atom, by sharing one electron with neighboring atom, it will form a covalent bond. Now, how we can change the conductivity of this semiconductor? In last lecture, we have seen by adding impurities. By adding impurities, we can change the conductivity of the semiconductor. Semiconductor divided into two types, intrinsic and extrinsic semiconductor. In intrinsic semiconductor, when we add some impurities like pentavalent and trivalent. In N-type semiconductor, we have added the pentavalent impurities. Now in P-type semiconductor, now we should add the trivalent impurities. Trivalent impurities like trivalent impurity like aluminum. Atomic number of the aluminum, we know that the atomic number of the aluminum is 13. Atomic number 13. In electronic configuration, in first orbit 2 electrons, in second orbit 8 electrons, and in outer orbit 3 valence electron. 2 and 8 and 3. In outer orbit, we know that 3 valence electron. Now, when we add some impurities in pure silicon crystal, here we add the impurities. Aluminum. Instead of silicon, we added aluminum. Aluminum having 3 valence electron. Aluminum having 3 valence electron in outer orbit, 1, 2 and 3. And fourth place, the deficiency of electron. Deficiency of electron means hole. Deficiency of the electron means hole. Aluminum having 3 valence electron, by participate with neighboring silicon atom, and it will share 1 electron and forms a covalent bond. And fourth place, at the fourth place, the deficiency of the electron means hole. The ability of hole, it will attract the electron. The ability of hole, it will attract the electron. Now, in N-type semiconductor, we know that in N-type semiconductor we added the pentavalent impurity. Here we added trivalent impurity. Trivalent impurity means in outer orbit only 3 valence electron, and at fourth place the deficiency of the electron means hole, and that hole which attract the electron. Now whenever we increase the temperature by applying potential difference across this silicon crystal, whenever we applying potential difference, when we increase the energy, the covalent bond breaks, and electron becomes free from the covalent bond, and that electron will participate to constitute a electric current. Now in n-type semiconductor, before we start the n-type semiconductor, we know that how much impure atom we should add in the pure silicon crystal. Means if we take pure silicon, if we take 10 power 6 pure silicon atom, then we should add only one impure atom. How many atom? We should add only one, means proportion ratio 1:10⁶. If we take 10 power 6 pure atom, then we should add only one impure atom. Then for 1 mole means Avogadro number means 6.023 into 10⁻23. We neglect the number, only we take the power. 10 power 23, Avogadro number to 10 power 23. How much electron? Do cross multiply. 10 power 23 into 1 divided by 10 power 6, which is equal to the 10 power 23 minus 6. 10 power 23 minus 6 means 10 power 17. Means whenever we are adding trivalent impurities in the p-type semiconductor, 10 power 17 electrons in n-type semiconductor, and 10 power 17 whole 10 power 17 holes in p-type semiconductor. P-type semiconductor means silicon crystal gets 10 power 17 extra holes, and ability of holes which attract the electron. Means whenever we are increasing the temperature, the number of electrons which are free from the covalent bond, that electron trapped inside the holes. Means in p-type semiconductor, the number density of hole which is too much greater as compared to the number density of the electron. Means number density of hole NH is greater than number density of electron. Means in p-type semiconductor, number density of hole which is greater than number density of electron. Means in p-type semiconductor, the majority charge carriers are holes. Majority charge carriers in p-type are holes, and minority charge carriers in p-type semiconductor are electrons. Majority in p-type semiconductor holes, and minority in p-type semiconductor are electrons. Number density of hole which is greater than number density of electron. Now band picture for p-type semiconductor. Band energy diagram or band picture for p-type semiconductor. Now at absolute 0 Kelvin temperature, at absolute 0 Kelvin temperature, energy level of valence band represented by EV and energy level of conduction band represented by EC, and between conduction band and valence band, between conduction band and valence band there is some gap that is represented by forbidden gap or energy gap EG. Now here we added trivalent impurities. In trivalent impurities, the ability of trivalent impurities that accept the one electron means here deficiency of hole. Because of deficiency of hole, it attract the one electron which free from the covalent bond. Means aluminum impurity accept the one electron from the crystal. That level is near about valence band. In valence band, number of electrons, and conduction band we can say completely near about completely empty in p-type semiconductor. Now for valence band, here we know that energy for silicon, that is 0.05 eV, and energy for germanium that is 0.01 eV. Here we use silicon crystal, that's why the energy is 0.05, and that energy available at room temperature we have seen in n-type semiconductor. Now acceptor energy level represented by EA, because here impurity, the ability of aluminum atom which attract the one electron, that's why acceptor EA represented by EA, and holes and electrons. Whenever we are increasing the temperature, what happens we will see later. Now this graph only true at 0 Kelvin temperature. At absolute 0 Kelvin temperature, all the electrons are in bound condition. The number of electrons 1, 2, 3, 4, all the electrons are in bound condition. Now what happens at room temperature? What happens at room temperature? Now at room temperature, band picture for p-type semiconductor at room temperature. At room temperature. Now at room temperature, valence band energy level, acceptor band energy level, and conduction band energy level. The current constitute only when the electrons are in more number of electrons are available in the conduction band. More number of electrons are free in the conduction band, and that electron, because of the movement of the electrons, it will constitute a electric current, and the electric current flows in the semiconductor devices. Now at room temperature, when we apply the potential difference across this crystal, at that time temperature increases. Because of the temperature increases, the covalent bond breaks. Because of the covalent bond breaks, and electron becomes free. Electron becomes free from the covalent bond, but that electron jump to the deficiency of the trivalent impurities, means that is aluminum. Here one deficiency, the ability of that hole to attract the electron, means the maximum electron which are free from the covalent bond are trapped inside the hole. Means we have seen here all the electrons are in bound condition. Now at room temperature increases, electron jump from valence band level to the acceptor band level, E A, in this way. Electron and little bit electrons can jump from valence band to the conduction band. Little bit electrons can jump from the valence band to the conduction band, and that number density of electron are very small, very little, it is compared to the acceptor band energy level. Means more number of electron except by the deficiency of the trivalent impurities. More number of the electrons are trapped inside the acceptor energy level, and only little bit electron can jump from valence band to the conduction band. That's why we are looking here only one electron in conduction band, that is insufficient to form a electrical current. That's why the number density of holes are more as compared to the number density of the electron. That's why in p-type semiconductor are very little bit electrons in conduction band, and current creates very little bit current creates in the p-type semiconductor, and that electrical current very little. That's why that is insufficient for any device to operate the device. Now p-type semiconductor, we have seen in p-type semiconductor, again I repeat quickly, in p-type semiconductor we have added trivalent impurities like aluminum having atomic number 13, electronic configuration 2, 8 and 3. In outer orbit only 3 valence electrons. Whenever we are added trivalent impurities, 3 electrons of the aluminum atom to participate with neighboring atom and forms a covalent bond, and 1 at fourth place, the deficiency of the electron, means hole, the ability of the hole which attract the electron. Now how many impure atom? Here aluminum, that is impure atom. How many impure atom we add in the pure silicon or pure germanium crystal? In pure, if we take 10 power 6 atom of silicon or germanium, then we add only one impure, that is aluminum. For 1 mole, means Avogadro number 6, approximately 10 power 23. How much impure atom do cross multiply? 10 power 23 into 1 divided by 10 power 6 is equal to 10 power 17. 10 power 17 extra holes gets the p-type semiconductor, silicon semiconductor crystal, means number density of holes which is greater than number density of electron. Majority charge carriers in p-type semiconductors are holes, and minority charge carriers in p-type semiconductor are electrons. Band picture. In band picture, acceptor energy level, valence band energy level and conduction band energy level. At absolute 0 Kelvin temperature, all the electrons are in bound condition. whenever we are increasing temperature, the electrons in valence band jump from the acceptor level. Only little bit electrons can jump from valence band to the conduction band. That's why that current is very little bit current, insufficient for any device to operate the device. Now we will see the recombination rate. Student, you can note down these p-type semiconductors, crystal and band picture, or you can take the screenshot also. Now we will learn about the recombination rate for intrinsic semiconductor and extrinsic semiconductor. Recombination rate for extrinsic and intrinsic semiconductor. Recombination rate. First, what is recombination rate? Question arises in our mind. Here we have seen the n-type and p-type semiconductor. Why? All the electrons do not jump from valence band to the conduction band. Question arises in our mind. Why all the electrons do not jump from valence band to the conduction band? The process is very rapid process. The creation of electrons and holes. Creation of electrons and holes and recombination rate at the same time. Process takes place at the same time, and whenever electrons and holes creates at that time, it will follow the laws of thermodynamics. It will follow the laws of thermodynamics and temperature. That's why it is not a very stable situation. It is not a very stable situation. At the time when electrons are free from the covalent bond, electron becomes free from the covalent bond. At that time, the tendency of the electron to move toward the positive side and tendency of the hole to move toward the negative side. And at the time of movement of electrons and holes, it will collide with each other. It will collide with each other, and it follows the laws of thermodynamics and temperature. Now the process at the same times means it take very little bit time. We can say microsecond or nanosecond. Means the recombination rate of and the creation of electrons and holes pair are at same time. Now we will see the recombination rate. The first one, the recombination rate for the extrinsic semiconductor. Extrinsic semiconductor. Recombination rate for extrinsic semiconductor. Extrinsic semiconductor means impure. Impure means n-type and p-type semiconductor. In extrinsic semiconductor, recombination rate is directly proportional to the number density of the electron into number density of hole, Ne number density of electron into Nh number density of hole. Here proportionality sign represent the coefficient of recombination rate. Proportionality sign, coefficient of recombination rate. Now if we remove the proportionality sign, Then recombination rate for extrinsic semiconductor is equal to coefficient of recombination rate. If we remove the proportionality sign, then we should place here capital R. R is the coefficient of recombination rate. Now recombination rate R into number density of electron into number density of hole. Now say equation number 1, recombination rate for extrinsic semiconductor R into Ne into NH. Now recombination rate for intrinsic semiconductor. Recombination rate for intrinsic semiconductor. We know that for intrinsic semiconductor, the number density of electron, which is exactly equal to the number density of hole, is equal to number density of intrinsic semiconductor represented by Ni. Ne is equal to NH is equal to Ni square. Now recombination rate for intrinsic semiconductor. Recombination rate is equal to coefficient of recombination rate R into number density of electron into number density of hole. Therefore recombination rate is equal to R into Ne into NH, Ne into NH. In intrinsic semiconductor, Ne is equal to Ni, Ne is equal to Ni into NH. In intrinsic semiconductor, NH, number density of hole, is equal to intrinsic semiconductor number density of intrinsic semiconductor. NH is equal to Ni. So NH is equal to Ni. R into Ni means recombination rate for intrinsic semiconductor. Recombination rate is equal to R Ni into Ni into Ni square. Equation number 2. From the laws of thermodynamics and temperature, from the laws of thermodynamics and temperature, recombination rate for intrinsic and extrinsic semiconductor. Recombination rate for intrinsic and extrinsic semiconductor are equal. Recombination of intrinsic and extrinsic semiconductor are equal. From equation number 1, recombination rate of extrinsic semiconductor, and equation number 2, recombination rate of intrinsic semiconductor, R into Ni square. Therefore equation 1 and 2. Compare equation 1 and 2 R into Ni square, which is equal to R into Ne into Nh. Therefore, RR, coefficient of recombination rate, cancel both the side. Therefore, Ni is equal to Ne into Nh. Number density of intrinsic semiconductor square is equal to the number density of electron into number density of hole. As per the laws of thermodynamics and temperature, the equation we have derived for semiconductors are Ni square is equal to Ne into Nh, which is very most important for examination point of view and for solving the sum of this semiconductor. Friends, today we have seen the p-type semiconductor and the recombination rate of extrinsic and intrinsic semiconductor, and the final result of the extrinsic and intrinsic semiconductor, recombination rate of the extrinsic and intrinsic semiconductor. Ni square is equal to Na into Nh. In next lecture, we will see the p-n junction. p-n junction means p-type semiconductor and n-type semiconductor. Whenever we are adding p-type semiconductor and n-type semiconductor, at that time what happens, that situation we will see in next video lecture. Thank you.